In the last example, I showed you about finding the slope of a tangent line given a couple of points. We took the secant line and we moved the 2 points closer together until eventually we had a tangent point. Now we're not going to do that whole process every time because that would be very tedious. So what we're going to do here is actually develop a formula to give us something to do that every time that it's kind of built into the process. And so I've got a picture here for you that's going to again talk about the secant line to start with. But you'll notice here that I have 2 points. Now here's the point that I'm really trying to find the slope of the tangent line. So as you can see, the secant line's a little steeper than what it's going to be eventually. That's one point. Now, the coordinates of that point are kind of important. The coordinates of that point are going to be an x and a y value. Now, judging by what we have here, it says f of x. F of x is the same thing as y, but then the x value, as you can see here, is x. And so for that point, I'm just going to call it x f of x. That's going to be my point at this dot right here. That's really the one that we're focusing on. But in order to find a slope, we have to have another point to connect it with, and that's going to be this one right up here. Notice that this one, the y value is f of x plus h. We have moved it over h units, whatever that happens to be, and that's going to change as we do this problem. So there's going to be a gap of h, so it's x plus h as the x coordinate, and f of x plus h as the y coordinate. So now we've got our 2 points, both just formulas at this point. We don't have any numbers going along with them, but we're going to use this to develop our formula. Now, overall, what we're trying to do is get a formula for what we call derivative. It's really just the slope of a tangent line at a particular point. We're going to use limits for this eventually. Now, the slope formula, as we know, is this in general. So we've got y2 minus y1 over x2 minus x1. Okay, so we're going to do that with these points that we have, and we're going to call this one, this point here, point 2, and this point, point 1. So if we're going to do y2 minus y1, we're going to do f of x plus h minus f of x to fill the top. If we're going to do the bottom part with the x's, it's going to be x plus h minus x. And so we're just going to fill those things in for the slope formula. It's just simply putting them in for y's and x's. Once we're at this point, notice that the bottom, we have x and we have negative x, so those actually can cancel out. We're just going to simplify this formula a little bit so that we have something that, well, is a little bit nicer. So the x's are gone, and it just makes h in the bottom, and this is the expression that we're really going to focus on here. This is sometimes referred to as a difference quotient. It's not the entire formula for a derivative, but it's part of the formula. It just doesn't involve the limits yet. Now, what we did on the example with the square root problem is we move these points closer and closer together. When we do that, when we get these points closer and closer together, h, this gap in between them, is going to get really, really small. So eventually this h is going to be 0. But there's a problem if that h is 0. If that h is 0, then we're dividing by 0 and it's undefined. So that divide by 0 problem still exists there, and we can't have that. So we have to use what's called a limit and get it as close to 0 as possible without actually making it 0. And so I'm going to flip the page here in a second, and I'm going to show you the only new thing is that now we're going to take this formula and we're going to put this limit out in front. The limit as h approaches 0 is what that's saying. So the limit as h approaches 0, it means as this gets infinitesimally close to 0, then we will have the actual slope of the tangent line that goes through this point right here. Well, we need to have specific examples for that. We're going to be going through specific examples, But overall, in general, the formula is then going to look like this. And this is what you could write down as your derivative formula. It's all of this stuff right here. This is what we just looked at. This f prime of x, that's the way to state derivative. When you see f prime, that means derivative of the original function. So this formula is going to be key for us in the next ones. Now this, you'll notice here it does say that this formula is true for all values of x where the limit exists. And so the next example, I'm going to show you just a couple of situations where a limit wouldn't exist. In general, we're going to just kind of trust this formula, but I will show you a couple that doesn't work with this one quite as well.